We're going to go ahead and get started. Looks like people are slowly coming back from. Our presenter is Kevin Rowland. So go ahead, Kevin.
Sure. Thank you. Can you guys hear me okay back there? Okay, good. Thanks.
Can I make one comment?
Sure.
So one of the comments from upstairs is if you're a presenter, try to keep the mic at a constant distance about 3 inches from your mouth. If you're having trouble upstairs, you have to keep adjusting the volume.
Sure. Thanks. Hi, everybody. My name is Kevin Rowland. I work at the Aerospace Corporation in El Segundo. I mainly help to build hill test beds for a few different launch vehicles. Spent some time writing software for a CubeSat program, and earlier this year, around March, I was writing flight software for a secondary payload that was slated to fly basically as an experiment on a larger vehicle. That was aerospace, designed, built, and operated. That program was kind of the genesis, excuse me, for this work that I'll be presenting today. Gonna skip the agenda real quick and just go to basically the bottom line up front. Really, it was just a week, a team of engineers at Aerospace spent that time building a proof of concept of a closed-loop test bed, but using QEMU, which is an open-source machine emulation framework to host an emulated flight computer. The 1 week is important. We actually only had 1 week to finish the work. It was funded by our internal innovation lab, basically. The iLab sponsors these so-called sabbaticals. They're short-duration projects for engineers to basically demonstrate the feasibility of a new technology. So it was a sprint to the finish, and we had some good results, hopefully. I'm going to start basically just by talking about QEMU. You've heard a little bit about QEMU, I think, from other presentations, in particular the high-performance spacecraft computing folks from OAR. But I know some of you probably aren't familiar with it, so I'm going to try to give a little bit of a more technical overview of the technology. QEMU, as I said, is an open source machine emulation framework that provides software models of most processor architectures, the more popular ones definitely. You might be familiar with QEMU in the context of a virtual machine, in which case it provides the ability to hook into something like KVM from Linux to emulate multiple machines running on one, for example, desktop class x86 processor. But it also supports so-called cross-platform emulation. That's basically where the host target is not equal to the guest target architecture, in which case it provides functional emulation of the machine, right? But it has to go through essentially a bytecode interpreter, so you're not actually running with cycle accuracy. And that instruction is done basically by another open source project called the Tiny Code Generator, which was folded into QEMU for runtime bytecode interpretation. It supports a variety of architectures, as I mentioned. I wanted to take the opportunity actually to look at the bytecode interpreter really quickly, just to kind of expose the fact that this isn't really magic. It kind of feels like it when you're running QEMU. On the left here is some thumb assembly code, ARM assembly code. It's actually taken from the flight software for the payload I'm talking about. This is actually the first non-branching instruction that's executed after reset. And if you go into the ARM architecture reference manual and you find the opcode, it's right here. And if you guys can read that, I know it's a little small, you can dig into QEMU and watch as the translator walks through the opcode bit field by bit field, basically, in order to get down to an eventual operation on the emulated CPU. I thought that was kind of cool to look at how it does this this translation from one architecture to the other. I know you folks know this, but it bears repeating, I think, before we start talking about developing peripheral models for this emulated machine, that an SoC, a system on a chip, is basically just a big memory map, right? For our particular machine, it was a ARM Cortex M0-based system on a chip. The Cortex M0 part of the emulation is fleshed out in QEMU. It's already supported. We didn't have to do that. We definitely couldn't have done that, let alone in the span of 1 week. So what we needed to do was basically capture memory reads and writes to peripheral hardware addresses, right? And to mimic the side effects of those peripherals. One thing that you got to keep in mind is that when you're mimicking the side effects of peripherals, in particular, low speed or simple serial peripherals like UART, I2C, and SPI, is that you can't necessarily pass those transactions down to the host operating system like you can if you were writing to video memory or something, in which case it would be passed down to the host video controller. So here's a little contrived example of basically just a UART write, right? You might disable the UART peripheral, stick some data in its transmit FIFO, enable it, and in real life, here's what happens. There's a side effect. There's a physical side effect. A wire gets wiggled, and on the other side of the wire, someone can catch that UART transaction and ingest the byte. When we're modeling our hardware peripherals, we can't exactly do that, right? We're constrained to a desktop Linux machine. We're not going to wiggle any wires. We're trying to emulate what happens with a UART transaction. So we have to think about how do we get that byte off of our emulated machine? Where does it go, and who can kind of capture it, right? So that's QEMU. I'm going to talk a little bit about this emulated processor in the loop testbed. It's good timing today to come after the talk from APL about the pill with the DART program, because that was a really good explanation of kind of what a hill looks like, what a sill looks like, what each of their pros and cons are, and what kind of a middle ground would be in between the two. So I'm going to repeat a couple of those things, basically. With an emulated processor in the loop testbed, you get this really big capability, which is you can run flight-like binaries on the emulated processor. Okay, so you don't need to do any surgery on the software in order to adapt it for commercial x86 machine. But you do avoid the high capital cost of real hardware, similar to the way that I think the Leon 3 was instantiated on an FPGA with the APL presentation. That's a little cheaper than getting real hardware. In this case, it's QEMU, it's open source, it's free to download, free to distribute, free to modify. So you get to maintain the ability to test like you fly, because you're avoiding flight software modifications, but you get the benefits of working in a pure software environment. The other advantages to an emulated processor in the loop testbed are that because you're running on a single Linux machine, it allows you to run multiple simultaneous simulations, right? The DART team talked about this too. When there's hardware, you have one piece of hardware, everybody contends for it, and not everybody gets to test when they need to test or what they need to test. With an emulated processor in the loop testbed, you kind of overcome that challenge. This is a quick look at kind of how an emulated pill sits in between a hill and a sill. The trades are probably more nuanced than this when you get to wondering what test bed you might want to make for your program. At Aerospace, we make test beds for a variety of programs. We're on contract basically for independent verification and validation. So we have to make these kinds of trades often when we're drawing up contracts or we're deciding what to do for a particular program. But I'm not going to go into real detail here, but you can see that an emulated pill sits in the middle in that it allays some of the issues with a hill and with a sill. So now I'm going to get to our actual project. That was just QEMU, the technology, and emulated processor in the loop, testbed, the technology. But what did we actually want to do, right? Basically, we wanted to use QEMU to model an ARM-based Virago VA10820. Virago Tech is a company out of Austin, Texas that makes radiation-tolerant systems on chip. In order to build a pill testbed for the spacecraft program I was talking about, which I can't talk too much about, and potentially because we might use this processor for our AeroCube CubeSat program. So we took modified control software originally developed for that spacecraft program, and we wanted to run that on the emulated processor. So we had to think about what do we have to fill out in the emulation so that the software runs unmodified and it thinks it's actually operating on an actual Virago. There was one small modification. It wasn't surgery to overcome the limitations of running on a sill or to rehost the flight software. Basically, all of our communication was over SPI. We decided to take one of the functionalities of the software and put that on an I2C bus instead, simply so that we could build out the I2C peripheral in the system on a chip in QEMU and exercise that peripheral. And then we use an existing vehicle simulation. It's called Frames. It's just an in-house simulation framework at Aerospace to provide the 6DOF vehicle model, basically, and simulated sensor measurements to close the loop. Here's the actual system on chip. Here were our goals. Some of these slides were from the proposal to iLab. So we're speaking kind of in the future tense that these are goals. We hoped to emulate these three, low power, simple peripherals because they would actually be used on the real flight software. And we were hoping we might get to something like timer emulation. We didn't. And here I've highlighted exactly kind of what we're going to do. We're going to want to write peripheral models down here to act like we're the hardware sitting at the end of the system bus, basically, reacting to register reads and writes and having some kind of side effect. What we want to do then is if there's a write from a SPI peripheral, we want to bridge that write over to an external simulation so that the external simulation can update its state. If there's a read from a peripheral model, then it needs to read data that has previously arrived from the simulation. That's the closed loop aspect here, of course. One thing I want to talk about a little bit, I don't know how familiar people are with QEMU. There are I2C bus emulations in QEMU. It's all baked in, but really what happens is when you write to an I2C peripheral, emulated peripheral in QEMU, and it gets put onto the emulated I2C bus, that all stays within QEMU. So you can talk to other devices that you might have defined in QEMU, but it doesn't really allow you to, punch out of the emulation and into the external world, which is what we needed to do because our 6DOF vehicle model sits somewhere else. It's a separate application. It runs separately. Could be running on a separate machine. It could be running right next to you on the same machine. But either way, it's not in QEMU. So we had to think of a different way to get this data out of QEMU's virtual machine. That's just another little overview, a little cartoon overview of what we're trying to do. And you can see, that we're wrapping it in one in that large box, which is just one single Linux machine. And that helps. All right, so what did we actually do? Well, we wrote some peripheral models as planned. We really just made it to the bare bones functionality. It was enough work to kind of dig into QEMU on a Monday, try to figure out how this large code base works, how to plug into it, so that by Tuesday or Wednesday when we were actually able to issue reads and writes from our flight software running on QEMU and see that they were actually making their way into our stubbed model, we didn't have much time to actually fill it out, but we filled out what we needed to, which is, enabling, disabling the peripherals, allowing for the transmit and receive FIFOs to be filled and flushed, right, from flight software. And that was for our UART peripheral, our I2C peripheral, and our SPI peripheral. I put some code on the side here too. It's small again, but it is always nice to see. I'm not going to go through it in detail right now, but if you get a hold of the charts afterwards, you can kind of look at it. You can also go into QEMU source code, of course, and look at how people model peripherals. Peripherals, obviously, they just hold some state. When a write transaction comes down to the peripheral register address space, the state might be mutated. The peripheral might have some side effects. That's basically what happens down at the hardware level, and so we need to emulate that. We needed to emulate that in QEMU, and we were successful in doing so. This is just a little, I've gone over this, that each of the three peripherals are used basically to communicate with the external simulation. This is a more detailed description of what exactly they do. The I2C bus was for transmitting motor commands to a gimbal, which was accomplishing pointing. SPI for receiving encoder measurements from the same motor, so you could close the loop, and have your control law actually close. And then UART was to receive ground commands, simulated ground commands, which allowed you to set a new set point. So you could see during a simulation run that setting a new set point resulted in the control law reacting and driving the motors to that new set point. That was a good way for us to show that we had accomplished what we wanted to accomplish in tying everything together. Okay, this was some of the more interesting stuff. I think one of the difficulties we had when we were writing these peripheral models. We decided basically to take any side effects that occur down at emulated hardware, package them up, bundle them up, and basically push them over UDP to some external user. Didn't matter who it was, whether it was some software just gathering the data to log it, or the actual 6DOF vehicle model on the other side. One thing we were interested in is basically minimizing UDP traffic, right? We don't want to react to every single byte that enters the transmit FIFO of a UART peripheral or an I2C peripheral or a SPI peripheral to result in a UDP transaction. That's a lot of wasted effort, basically, when you're sending long strings of bytes over a UART peripheral. So you want to think of some communication heuristics, right? When do you decide that your transmit FIFO is full enough that you want to package that up and send it over to the external simulation? For I2C, it was really easy. The I2C specification actually talks about, the ability of the transmitter and the receiver to know the length of the transaction beforehand. It uses an explicit start bit in the command register to kick off a transaction, and an explicit words data word in another register in the peripheral to tell it how many words it should expect to send or receive. For the SPI peripheral, it's a little more difficult. You really just send bytes down to it, and they're supposed to, in real life, obviously, just wiggle the wire, and they're sent off to the other side. Luckily, we had this mode in the SPI peripheral called block mode, which accomplishes something similar to the I2C peripheral, which is that you can tell a SPI peripheral to wait, hold off, until the transmit FIFO is full of a couple of different words. Then you can tell it to start. It'll send all the words at once, and we use that to our advantage to minimize UDP traffic. And here are some results. I think we'll probably kind of blow through these, but they were a good way for us to show to our funders, iLab, and to our management that what we were doing actually worked and that it might be useful for a closed-loop test bed in the future. I mean, there's not much to look at here. The control software executed its algorithm correctly. We could send new set points. So a new set point was sent around here. You can see the control software, I think it's just a PI loop, overshoot, and come back down to the new set point given encoder measurements from the 6DOF model. This is kind of just a repeat. Set points received from the ground, proof that the emulation worked as expected, proof that our peripheral models worked as expected. We didn't have to modify anything in flight software that actually talked to the real peripheral models. We didn't have to modify any of that in order to actually send data from our emulated peripheral models. So that was good. And then this proof of concept of a way to bridge from our emulated peripherals onto the host machine's network in order to send data off to an external user. Okay, this isn't working. Could I go to the next slide, please? Next slide. Can someone, yeah, thanks. This is the last slide. This shouldn't be the last slide. I can talk though. Uh, uh, did it jump? Yeah. So there. Good. Okay. There are more slides. I hope. All right. Um. Right. So some more cool things we demonstrated. One of the advantages of using this emulated processor in the loop, right, is that you don't have to contend for hardware. You can run multiple simulations at the same time. If you want to do many dispersions at once, if you want to run Monte Carlo runs, you can do that. But again, you're running on modified flight software, which is nice. We demonstrated that. We had some hokey solutions for doing that, but that was just due to time constraints, things that you could pretty easily manage to fix in the future. Good. Okay. So some future work. We left a lot on the table in terms of emulating the Virago system on a chip fully. Right, we focused on those 3 hardware peripherals so we could get data running back and forth between the emulated machine and the vehicle model. So we need to do a lot. We need to do a little bit more of the system configuration, or emulate more of the system configuration. The Virago exposes a variety of special registers to control its state or how it operates. We did not get to sending interrupts up to the emulated CPU core, but there's a framework in QEMU to do that. It looked a little daunting. It was Thursday and we didn't have time to do it as we were wrapping up and generating some results, but that would be next, I think, on the table. Same with GPIO. I think it was relatively simple. You want to send discretes or bilevels out to an external simulation, you need to model your GPIO peripheral to do that. Timers and counters are really important, obviously. If you have, we're running a bare metal with no operating system, so we have a big event loop timed off of some periodic, I think, 10 hertz timer. We weren't able to emulate that, so we had to tweak the existing flight software a little bit. Oh, sorry about that. Actually trying to go back, there we go. I talked about this a little bit. I had a whole slide for it just in case there was some more time. But there's this open question: when do we package words for transmission over UDP? We don't want to do it that often. A similar analogy is with something called a VM exit, which is an instruction for virtual machines to basically exit out of their code, go down to the hypervisor, and allow the hypervisor to do its thing to switch between virtual machines. There's been a lot of work in QEMU to minimize VM exits. They're costly, right? It's a similar thing here. We know UDP transactions are a little costly, so we'd rather not be doing them for every single byte that hits the peripheral. I'm going to speed through these. I have 2 minutes left. Future work would be actually potentially containerizing this entire test bed with something like Docker. I don't have any experience with it myself, but because it's pure software, it's doable. It means you could send it up to the cloud potentially. You could run it on a variety of servers. And that's a real useful thing when you're trying to test your software exhaustively. There's some future work with, actually speeding up the sim. We weren't able to tell if we were running faster than real time. We weren't able to tell if that would still be the case when we had emulated timers firing at, at virtual 10 hertz. But we can do some things in Linux to basically speed up the application. And then I think this big bullet point's really important. Obviously, do we run faster than real time is important, but do we run proportional to real hardware? We're kind of selling this as an emulated processor. It should feel like the processor. Do our algorithms take approximately the same percentage of our allocated control cycle, whether we're running on real hardware or emulated hardware? We don't know. That would be a good analysis to do. And then, is it worth it? Remains to be seen. This is kind of an aerospace specific slide. We do a lot of program work for a variety of programs. We have to decide to what level of fidelity we want to actually test contractor software. So we have to think, do we want to buy a development kit and just kind of fake things out that way? Do we want to build an emulated processor in the loop? Or do we want to do a pure software in the loop test bed? With some of these cheaper processors, it's obvious. You just buy the development kit, get the hardware. You can get 10 of them or something for your testers, and then install some open source tooling. If you want to test like you fly with something more expensive, something a little bit more difficult to obtain, the emulated processor in the loop might make sense. And that's it. Yeah. Thank you.
Do you have any questions? Questions?
So I just have a clarification question. So you are running QEMU on a virtual machine then and emulating a board?
Sorry, could you repeat the question?
So you are running QEMU in a virtual machine, and you are saying that it's running faster than real time?
So it's not running in a virtual machine. QEMU is creating a virtual machine. It's running as a user space application on Linux, and it's just mimicking the entire system on a chip. That itself is the virtual machine. There's no additional layer.
And it's running faster than real time?
Correct, yes. Faster than real time, right? Because our desktop Linux box that's running QEMU is running at 1.5 gigahertz or something. And this small Cortex M0 based system on a chip runs at, I think, 200 megahertz. So we can blow through a ton of ARM instructions in less time than it takes for the real system on a chip, simply because our Linux processor is so powerful. And QEMU is well done, honestly.
Thanks.
Mm-hmm.
Thank you.
Yeah.
That's all we have time for.
Sure.